Hello, it's Keith here, and this is lesson 83 of the platform-specific series of my Z8 assembly programming tutorials. Now, we're going to be looking at the Spectrum Next today, and what we're going to be looking at is at the Mintile program, which is my multi-platform software tile map. Now, on the Spectrum Next, we're running the system in 256 color layer 2 mode, and we've got our object moving around the screen here, and we've got XFlip on the Sprite objects, and we've got the scrollable tile map, which is scrolling 4 tiles there. Now, we're going to be looking at the code that does this today, and as I say, this is a piece of code that works on multiple systems in the same way. A lot of the code is actually shared among all of the systems, and so you want to see the Mintile series, which covers that shared code, and it's just the platform specific code we're going to be looking at today, which is basically the code that relates to the actual drawing of the bitmaps onto the screen. Okay, so we're using the so-called layer 2 to actually draw our graphics, and so we're initializing layer 2 here. Now, the way that I've come to use layer 2 on my programming, the way I've found best, that is to page in part of the VRAM into the memory area from 2000 to 3FFF. Now, the reason I do this is because this allows us to use interrupt mode 1, which is far easier than the interrupt mode 2 we're forced to use on the ZX Spectrum Classic. So we use NextReg51 to page in part of the memory into this range here. Now, this splits the screen into 6 parts. The screen itself is, I think it's 48 kilobytes in total, and so we're paging in 8 kilobyte blocks, and we're working on those individually. Now, each of our tiles is 8 by 8 pixels, and so on the Spectrum Next, I've actually put a limitation in which is somewhat substandard, should we say, that the sprites are actually only moving down in and up and down in 8 pixel blocks. They're moving across the screen in pairs of pixels, but they only move up and down in 8 pixel blocks. Now, that is vastly inferior to what the Spectrum Next can do, but for the purposes of today's example, I thought that was good enough, because on some of our systems we have that as a hard limitation anyway, and so I thought it would be acceptable in this case, because it made the banking issue much easier, because we only needed to worry about banking in at the start of each tile, rather than if we were halfway down a tile we might need to page in a different memory bank on each line, so that would have slowed things down and made them a little bit more complicated. So for the purposes of this minimum tile example, we are limiting our Y movement to exact tiles. Now, once we've paged in the VRAM at the start of our program, most of the code here is actually just the test code, which I'm not going to cover here because it's covered in the multi-platform series. So what we're actually going to look at today is the code that actually handles the drawing of the tile map to the screen. Now, the way Mintile works is most of the code is actually multi-platform, and it's just this do strip routine that you can see starting here, which does the actual platform specific part. Now, what this does is we split our tile map, whether it's the entire screen or a simulated sprite, into a series of strips, and each one is horizontal, and we draw them and we move down the screen and we build up whatever it is we're trying to draw in that method. And so the only part of the code that's platform specific is do strip, and this is heavily optimized for the system we're drawing on, but the rest is multi-platform to reduce the amount of code we have to port to cover a new system. Now, this is the Mintile example. I'm working on a more advanced one, which is called Max Tile, and I will try and get more smooth movement vertically for that one, and I'm doing some other things as well. But for today's example, it's just a little bit simpler. So this is actually going to use self-modifying code, and it's going to use stack misuse. So what we're doing here is we're backing up the true stack pointer for the length of this strip. Now, what we're doing then is we're paging in the shadow registers, and we're loading in a tile number from BC here. Now, this is the tile number from 0 to 255 that we want to show. Now, Mintile uses tile 0 to be an empty tile. This either means in a sprite, a transparent part of the sprite, or for the tile map is actually a cache of updates, of changes, and so a tile of 0 there means that nothing's changed, so nothing should be drawn. Now, in the case of a non-zero tile, we're loading that into H here, and then we're writing a value of 0 into BC here, setting the tile to 0 for next time in the cache. But if we're drawing a sprite, we don't do that, and so what we would do in that case is we'd use self-modifying code to replace that load BC, A with a no operation. Okay, now what we're going to do next is we're going to select our bitmap memory for the source pattern of our tile. So what we're doing here is we're basically multiplying the tile number by 64. It's 8 by 8, the tile pattern is, and each of the pixels is a single byte because it's 256 color mode we're using here. So we're calculating that, and we're adding the DE base here. Now, DE would point to the pattern data in memory when we run this routine. Now we've got a loop counter because the code is a little bit long here, so just to save a bit of code, we are using a loop instead. And so what we're going to do is basically we're going to draw the entire tiles to the screen. Now first though, we are backing up H&L into BC here for later. Now what we do is we do a pop DE that loads in 2 bytes and effectively 2 pixels, and we transfer those 2 pixels to the HL VRAM destination here. We're inking L after each time moving across the screen. So we do 8 bytes for one line of our tile. We then reset the L part of the HL VRAM destination and we ink the H part. Now that is effectively moving us back to the left hand side of the tile and moving us down one line. We then do the same again for a second line, and we repeat this 4 times, so that we've got our loop there repeating 4 times. Now once we've done that, basically what we're doing here is we are then resetting our H part, so we're moving back to the top of the tile, and then we're adding 8 to the L part of the VRAM destination, moving across to the next tile position, and then we're repeating for all of the remaining tiles before restoring the stack pointer and returning to the calling routine. So this is used for either drawing the entire screen or drawing a simulated sprite, which is a miniature tile map. Now in the case of a simulated sprite, we need to calculate the VRAM destination, and so this will be passed an XY coordinate in B and C. Now this is in logical units, which on all of my systems now I work in pairs of pixels, so one logical unit is 2 pixels, and this is so we can have a nice 8-bit coordinate that allows for off-screen areas on a 256 by 192 screen. So that's why I use that coordinate system. Okay, so what we're doing here is we're limiting the Y coordinate to a full tile here, and that's for convenience because it makes this code a lot simpler for moving down a line within our VRAM. So that's why we're doing that. Now what we're then doing is we are converting the X position into pixels, and we are basically going to calculate the Y line within the bank. That is the part of the Y coordinate that is the offset within the current bank of VRAM. And then we are basically selecting the VRAM destination so that it starts from 2000 and goes to 3FFF. That's why we're ORing in that bit there. That would be the 2 part of the 2000. Okay, and so we're loading that VRAM destination there, and then what we're doing here is we're taking the 3 remaining bits of the Y position, and these are effectively the bank number. And so what we're doing here is we're shifting them into the correct position for the banking, and then we're adding 16 to move to the first default VRAM bank, and we're using next reg 51 to page in that VRAM bank. Now this all works fine for the tile, and because the tile is always within the same bank, we don't have to worry too much. But what I will do next time is I will have to put in some more advanced code in my ink HL part here, which will actually have to check if we've gone over a bank and page in the next bank. But that is that's outside of what I'm trying to do here. This was a very minimal tile map system, and as I say, it's not. It wasn't a requirement for my purposes for this that it allowed for smooth vertical movement. And as I say, this is a sort of a midway point to the max tile solution, which I'm currently developing, which will allow XFlip, Y-flip. It does transparency, it does lots more things. And so I'd say this is just a crude version that's a sort of stopgap measure. Okay, now Mintile doesn't support Y-flip, but it does support X-flip, and the reason for that is this was used for a little game I wrote called Chibi Fighter, which was a Street Fighter clone. And if you've ever played the original Rise of the Robots, you'll know that you need to be able to make your characters flip around horizontally so that they can turn the other direction, which Rise of the Robots could not do, and thus sucked quite badly. Okay, anyway, so enough insulting of very old games. So what we've got here is a routine that will draw the tiles reversing the pixels, which on this system is very easy because the pixels are single bytes. So all we're going to do is do the exact same thing of loading in our source tile, calculating our pattern source and loading that into the stack pointer, and then we've got our loop here. It's basically very similar. The only difference is really going to be that instead of inking BC to move across the source tile map, we're decrementing it, moving in reverse from right to left in our tile map. And then after each pixel is drawn to the screen, we decrement the L part. So we're going from right to left. We're still reading the source data in the same order. We're drawing it to the screen in the reverse horizontal order, and that will XFlip our sprite. Nice and straightforward there. So that's all we're doing on this system. It's pretty straightforward. On a lot of the systems, it's actually a lot more complicated because if we've got multiple pixels per byte, we have to do things like lookup tables or some kind of bit shifting, a lot of a pain. But on this system, because there's so little data and it is only 1 pixel per byte, it's very easy, but of course lots of source data, so might have to deal with some bank flipping. Okay, anyway, as I say, this is the end of the Mintile for this Spectrum Next, but we're going to come back to the Spectrum Next with the Max Tile routine, which I'm currently developing, and that's going to be far more advanced and fix most of the issues, hopefully, with Mintile, and that's I plan for that to be used in any future games I write. Anyway, hope you enjoyed what you've seen today. Thanks for watching, and goodbye.